Hello everyone. So today we're going to look at section 14.4, differentials and local linearization. We first define what we call total differentials. So if you have a function z of two variables, x and y, dz, the differential dz is equal to the partial of f with respect to x times the differential dx plus the partial of f with respect to y times the differential dy. And then we extend that to a function of three variables. So w is a function of x, y, and z. So basically same idea, dw partials with respect to x of times the differential dx plus partial of f with respect to y times the differential dy. And then finally add on the partial of f with respect to z times the differential dz. So a pretty simple situation. You just have to find the respective partials. So assuming z is a function, we could see z as a function of two variables here. And so we'll say the partial of z with respect to x, we'll just call it f. Sub x is differential derivative of x to the fifth, 5x to the fourth, tag along the y to the fourth. Partial with respect to y. X is a constant. Y to the fourth differentiates to be 4y cubed. So 4, tag along the x to the fifth, y cubed. And if you want to rewrite the differential form, dz is f sub x dx plus f sub y dy. So just simply substitute. So 5x to the fourth, y to the fourth, dx, plus 4x to the fifth, y cubed, times dy. So a fairly simple example. And here, just an extension to the three variables now. Pretty much the same concept. Get the partials. So we get 3x squared, y squared, c to the fourth, for the partial with respect to x, partial with respect to y, 2x cubed, y, c to the fourth, because note that for x, y and z are held constant, so you can cover those up, and the derivative of x cubed is 3x squared, and then tag along the y and the z factors, f sub y. X and z are now constant, differentiating y squared, we get 2y. So, and then tag along the x and the z factors. And similarly, partial with respect to z. X and y are now constants, derivative of z to the fourth, 4z cubed. So 4, tag along the x cubed, y squared, and z cubed. And then if you want to write down the definition again for the partial. There it is, and just substitute. Okay, so finding total differential is pretty straightforward, and we'll move on to what we call local linearization. And what we do is we actually approximate the function by what we call the local linearization, which we'll see an interpretation of that in a figure in a moment. But the idea is that the function is approximated by this L of xy is going to be a point on the function, so that's what f of x sub 0, y sub 0 is. That's a point on the function. And then plus the partial with respect to x evaluated at that point times the quantity x minus x sub 0, and then plus the partial with respect to y evaluated at that point times the quantity y minus y sub 0. And then here, for future situations, we noted that if we transpose this f of x sub 0, y sub 0 to the left, we get f of x y minus f of x sub 0, y sub 0, which we're going to call delta f. That's just the change in f, and that would be the remaining two terms on the right side. And that allows us to then say that delta f is delta z, and that delta z is the differential dz, and that delta y is the differential dy, and delta x is the differential dx. So an interpretation of the idea is that you have some surface, let's say this is my surface, and I call that surface f of xy. And then you have a point on the surface, and that would be our point x sub 0, y sub 0. And then you basically get the tangent plane to that point, and that's what the linear approximation is. This is L of xy is really the tangent plane at that point. Okay, so this example will further illustrate that concept. So start with a given function, a point P, and then a point Q that's pretty close to P, and it says find the linear approximation of the function at that given point. So if we look at the definition for the linear approximation, I'll rewrite it here. L of xy is the function evaluated at x sub 0, y sub 0, and then plus the partial with respect to x evaluated times the quantity x minus x sub 0, and then plus the partial with respect to y evaluated at that point x sub 0, y sub 0, times the quantity y minus y sub 0. So first thing we could do, and this is the point P is the x sub 0, y sub 0. So the first thing we could do is, let's say, evaluate f of 1, 0. And f of 1, 0 would be x is 1, y is 0, so 1 times e to the 0, that's 1 times 1 or 1. Then we could evaluate the two derivative partials, f sub x, partial with respect to x, and the partial with respect to y at that given point. So f sub x of xy is, okay, we're going to find the partial with respect to x, so y is held as a constant, derivative of x is 1, e to the y tags along, and then evaluate that at the point 1, 0. And this means that x is 1 when y is 0, so e to the 0, which is 1. And then we'll do f sub y of xy. So that's the partial with respect to y. And we're holding x as a constant. And the derivative of e to the y is e to the y, so that's just x e to the y again. But then that evaluated at the point 1, 0. X is 1, y is 0, so 1 times e to the 0 is also 1. So then we substitute into the definition. So L of xy is the value of the function, 1. It's f of 1, 0, plus f sub x, which was 1, times x minus x sub 0 was 1, because this is the point, 1, 0. And then plus f sub y, which was 1, times y minus y sub 0 was 0. And so L of xy is 1 plus distributing x minus 1 plus y. So L of xy is the function x plus y, which is basically the tangent plane here. And now, to further make sure that we understand the concept, oops, sorry. We're going to approximate that function at q. So the point q, recall, was 0.98 and 0.2. Actually, I want that to be 0.02, I'm sorry. So we're going to change that in the given problem as well. That's my mistake. We want this q to be 0.98, 0.02. So please make that correction. And so q is going to be the point, again, 0.98, 0.02. Notice it's arbitrarily close to the p, which was 1, 0. And recall that our function f of xy was x e to the y. So if we want to approximate f of xy at q, f of 0.98 and 0.02 just simply means to plug in a 0.98 for x, so we get 0.98 times e to the, plug in a 0.02 for y, and go to your calculator, and I came up with 0.999 999 79 7313. Okay, and that's the function. And the linearization, L of 0.98 and 0.02, well, remember that L of xy was x plus y, so that's 0.98 plus 0.02, which is 1. So basically what we have in terms of our little figure here would be the surface. Okay, that's your f of xy. The point P, you got the tangent plane, and you got a point Q that's really, really close to point P. And we're finding the difference in the heights between what's on the surface, f of xy, and what's on the tangent plane, L of xy. So here it says to find the error of the approximation. And so the error is just going to be the difference between f of xy, or let's say f of 0.98 and 0.02, and the linear approximation of 0.98 and 0.02, which was the 0.997 sorry, 97313 minus 1, which would be a negative 0.000267. And then it says compare it to the distance from P to Q. Well, the distance is just going to be the square root of the difference in the coordinates, 1 minus 0.98 quantity squared, and then 0 minus 0.02 quantity squared, so that's just simply our distance formula. And we get the square root of 0.0008. Care to crunch that down. And so if we make the comparison, so you'd see that basically the point Q that's on, if we call that Q and we call this P, the point Q that's on the tangent plane differs from the actual point on the surface by this amount of error. And then we calculated the distance from P to Q, and now we're going to compare that distance to the error. So if we take the error over the distance, we get that 0.000 202687 over the square root of the 0.0008, and we get a pretty small number here, 0.00716606 is what I got. Okay, so it gives us a good interpretation of how we can approximate the function using the local linearization. Alright, the final problem in this section, and I think we can finish it in a reasonable amount of time here, is just a little word problem. It says the radius of an altitude of a cylinder is measured to be 3 inches by 8 inches respectively. Possible error of measurement of 0.05 inches. And it says use differentials to approximate the maximum percentage of error in the calculated volume. So the idea is that you have this cylinder, so a little can of soup or whatever you want to call it, and you've got a radius and an altitude, and they could differ excuse me, by as much as the actual measurements can differ for the radius by 0.5 inches, so we'd have a larger radius, and similarly the altitude can differ by 0.5 inches as well. So if you draw a little, almost like an outside casing, okay, that distance there would be the differential dr. And then this distance here would be the differential dh. So you can see they can have, and that could go inside as well. Okay, so you'd have, you know, a bigger can, but you want to approximate the volume, the maximum percentage of error in the volume. So we start with the fact that when we have a function z is f of xy, then the differential dz is f sub x dx plus f sub y dy. And if our volume function is pi r squared h, the volume of the cylinder, then the differential dv is going to be the partial of v with respect to r times the differential dr plus the partial of v with respect to h times the differential dh. Or I guess it could have said v sub r. Similarly here, I chose to use the differential notation. Instead, but similarly we could have said dv is v sub r dr plus v sub h dh. I like this version because you can kind of see it just a little bit better in terms of their total differentials. So in any event, let's find partial v with respect to r, and that's going to be 2r, so 2 pi r h. Partial v with respect to h would be, r is a constant, so is pi. Derivative of h is 1, so just pi r squared. A couple things I forgot to write down was that the radius is given to be 3 inches, the altitude is 8 inches, and another thing we could say is that the differential dr is equal to the differential dh, which is plus or minus 0.05 inches. So then we can go to our formula. The differential dv is dv dr, so that's 2 pi rh times dr, and then plus dv dh, that's pi r squared, times dh, and now it's just a matter of plugging in. You got 2 pi times r was 3, h is 8, dr, the plus or minus 0.05, and then plus pi times r again was 3, that has to be squared, times dh was the plus or minus 0.05. So if you crunch this down, I came up with plus or minus 2.85 times pi, which is plus or minus 8.95, and that would be inches cubed because it's a volume. So with those little small error of measurements of 0.05 inches each in the radius and the altitude, if they were both positive 0.05 bigger, you'd have that much more volume in the can. Okay, so that's it for lesson 12.4. We'll see in a little bit with, or 14.4, excuse me. We'll see in a little bit for 14.5.